All right, chemistry. Let's start chapter 4, section 3. Okay, this is the big daddy of this particular chapter, Electron Configurations. So let's go ahead and get started. We have three large objectives for this section. One, list the total number of electrons needed to fill each main energy level. Now that is something that we can already do, right? The equation 2n squared. As long as we have the n value, the principal quantum number, which represents the main energy level, we can simply plug that in to 2n squared, and we can know the total number of electrons needed to fully occupy each main energy level. We'll see that we don't fully occupy each main energy level all the time, but we'll cross that bridge when we get there. Second, there are three rules that we need to learn. So state the off-bow principle, the Pauli exclusion principle, and Hund's rule. Three very, very important rules. If you can remember those, it's going to make this next objective very easy. Describe the electron configurations for an atom of any element using orbital notation, electron configuration notation, and, when appropriate, noble gas notation. Again, three different notations, three different rules. It's going to make it a lot easier on you. Let's start with electron configurations. Now, if we just look at the basic words there, electron configurations. Configuration, it's the arrangement of electrons in an atom. The arrangement of electrons within an atom. Now, the lowest energy arrangement of the electrons for each element is called the element's ground state electron configuration. Okay? If we don't have any excited electrons whatsoever, every single electron is in its lowest energy state, as low energy as is possible. That's considered the ground state electron configuration. Now, looking at relative energies, okay, when we get especially to the off-bow principle, we're going to see that as we fill certain orbitals, each successive orbital is higher and higher and higher energy. So here with this this picture, this diagram right here, you want to refer to this in the future. This is the order of increasing energy for atomic sublevels using a vertical axis with energy on that y-axis. Okay? Each individual box represents an orbital. So let's refer to some things we've already covered in section 2. 1s, right? Why is this called 1s? There, of course, is only one s here, but this is when n is equal to 1. All right, so this is the s orbital, the single s orbital that is present at n is equal to 1. If we go up one n value, one main energy level, one principal quantum number, we have another s orbital, but since n is equal to 2, we call this 2s. It's the 2s. Now, there's still only one of those orbitals, but as we see, when we have our p orbitals, we have 3 p orbitals, okay, 3 p orbitals, but these p orbitals are found within n is equal to 2. So these are the 2p orbitals. Next up, 2, n is equal to 3, right? So we have our 3s, 3p, and then this is going to get a little tricky when we start to fill these in order. We have the 3d. One thing that's a little bit annoying, okay, this is totally annoying. You guys aren't going to like this. I understand it. It's just one of the things we got to deal with. If you were to look really, really closely at this energy line right here, okay, for the 3d, for the 5 3d orbitals, if we trace that over, we're actually going to see that the 3d orbitals are actually slightly higher energy than the 4s orbital. Okay, that's really important because when we look at the off-bow principle on the next slide, we're going to see that we have to fill the lowest energy orbitals first. So even though we got 3s, 3p, and 3d, because the 4s is lower energy, we're actually going to fill 4s before we fill 3d. So we're going to fill 1s, 2s, 2p, 3s, 3p, 4s, then 3d, onto 4p. Okay? But again, look, we're going to have to go to 6s before we fill 4d. Okay, and I know it's annoying. I know it's frustrating. It's just one of those little nicks that we're gonna have to learn. So, like I promised, the Aufbau principle. Aufbau is actually a German word that means to build up or building up. It's not a name. Okay, a lot of people think it's some person's name. It's not. It's actually German for building up. So according to the building up principle, the Aufbau principle, an electron occupies the lowest energy orbital that can receive it. Okay, like I was saying, we have to fill the lowest energy orbital available. Next, according to the Pauli exclusion principle, no two electrons in the same atom can have the same set of 4 quantum numbers. Now, this really becomes an issue when we look at spin number. And I know we didn't talk about spin. We didn't delve into spin all that much, but it's using the Pauli exclusion principle and making sure that no 2 electrons have the same 4 quantum numbers, right? They can have 3 of the same, but as long as that spin number is different, we're okay. And so it's really going to come down to how we use the spin number, up spin or down spin, plus half, minus half. All right, next up, according to Hund's rule, orbitals of equal energy are each occupied by 1 electron before any electron is occupied by a second electron. And all electrons in singly occupied orbitals must have the same spin state. Okay? Now, like we covered in section 2, we can definitely fit 2 electrons into every single orbital. That doesn't mean we're going to fit 2 electrons into an orbital before we move on to the next orbital. Hund's rule actually says we're going to fill each orbital with 1 electron before we double up in any particular orbital. And then lastly, when we go to singly fill all of the orbitals with 1 electron, they all need to have the same spin state. Okay, same spin state, and then we go back and we add a second electron in each orbital of the opposite spin state.
All right, when you're filling electron energy level diagrams like this one, you have to obey 3 different rules. They are the Pauli exclusion principle, the Aufbau principle, and Hund's rule. The Pauli exclusion principle says that no 2 electrons in an atom have the same 4 quantum numbers. The Aufbau principle means fill from the bottom up. Orbitals of the lowest energy are filled first, from the bottom up. And Hund's rule says that if you have multiple orbitals of the same energy, put 1 in each before they double up. In this case, P has 1, 2, 3 different orbitals. 1 goes in each one before you double it up. A common question you might find are, which of the 3 rules does this electron energy diagram violate? Well, here in the 1s we only have 1 electron. You're not allowed to fill upper orbitals until you've filled all the lower ones in a ground state atom. This violates the filling from the bottom up principle, or the Aufbau principle. You can't do that. Let's see what we have here. Here, we've filled from the bottom up, so that's good. And we've even put 1 in each of the P's. But what I notice is that we have 2 electrons in the same orbital that are both spin up. That means N is the same, because N equals 1. L is the same. It's an s orbital, so L is 0. ML, when L is 0, can only be 0. And if they both have spin up, that means their MS's are the same too, both positive a half. Here we violated the fact that no 2 electrons can have the same 4 quantum numbers. They're both spin up in the same orbital. You can't do that. This violates the Pauli exclusion principle. It excludes you from doing this kind of crap. What does this violate? Well, you can probably guess it violates the Hund's rule, because it's the only one I haven't done so far. But take a look. You need one in each of these p's before you double up. That's the key here. 1 and 2 here, 1 here is 0. No, spread them out. This violates Hund's rule. You can't do that either. The question becomes, how do you even do this properly? Well, you'll notice each of these had 7 electrons. So I'm going to put 7 electrons in here properly, according to the 3 rules. Number 1, no 2 electrons need to have the same 4 quantum numbers. Number 2, fill it from the bottom up. Number 3, spread them out before you double them up. So, 1, 2, 3, 4, 5, 6, 7. Went from the bottom up. I made sure each of these had 1 in it before I started doubling up. And I made sure 1 was always up and 1 was down. Follow the rules and draw your electron orbital filling diagrams properly. Don't not spread them out. Don't have 2 spins the same in the same orbital. And don't not fill a lower orbital before you start cramming them in the top ones. Best of luck.
Yeah, that guy's super cranky. We're not going to be that mad when we do it. Anywho, we are going to cover one of the types of electron configuration before we finish up this first part. It's called orbital notation. Remember, your third objective for this section is to represent the electron configuration for any atom using orbital notation, electron configuration notation, and then noble gas notation. We're going to leave electron configuration notation and noble gas notation for next lecture, right? Part 2 of this section. We're just going to look at orbital notation, which is a type of electron configuration. Like that's what we're showing, but we are looking at it from the perspective of arrows. Okay, so an unoccupied orbital is represented by a line. Okay, just like we saw with the cranky guy going through those different rules. He drew a simple line, and he wrote the orbital's name associated with that line. 1s, 2s, 2p, 3s, 3p, and on and on and on. And so an orbital containing 1 electron is represented by an up arrow, right? That electron is said to have an up spin, right? Plus 1/2. All right, so anytime we have an empty orbital, we do need to draw the line. Okay, we do need to draw the line, even if there is no electron in it. We still need to draw the line, but we're just going to have nothing above the line. If we were to draw this orbital doubly filled, right, because they can hold 2 electrons, if it actually does have 2 electrons, we would simply draw a down arrow right next to it. Continuing with orbital notation. An orbital notation, like we said, that contains 2 electrons is represented by having 2 arrows, 1 pointing up, 1 pointing down. Now, the lines are labeled with the principal quantum number and the sub-level letter. For example, if we're going to write the electron configuration in orbital notation for helium, we're going to write our line, we're going to write sublevel S, and the quantum number here is 1. The principal quantum number here is 1, so 1s below that line. And helium has 2 electrons. How do I know? It's got 2 protons, and we're assuming that these are have no overall charge, that they're neutral.
Electron configuration can be indicated by orbital notation. In orbital notation, an unoccupied orbital is represented by a line. The lines are labeled with the principal quantum number and sublevel letter. An orbital containing 1 electron is represented by a line with 1 arrow pointing up. An orbital containing 2 electrons is represented by a line with 2 opposed arrows, showing the electrons paired and with opposite spin. Look at the superscripts for each orbital in the electron configuration. The superscripts indicate the number of electrons in a given orbital. We add arrows to show these electrons. Once all the electrons have been placed, the orbital notation is complete.
All right, guys, we're going to cut it off there. We've covered orbital notations. We still have electron configuration notation as well as noble gas notation to cover next time. That'll be a lot of fun. Hopefully from last section, you can calculate the number of electrons required to fully occupy a particular main energy level, right? That's our first objective. And we also covered the 3 rules governing electron configurations, okay? All right, guys, I will see you next period.